exploring the practicality and impact of ordinary differential equations in real-world applications. Introduction to ordinary differential equations and in the realm of mathematics, ordinary differential equations provide a practical framework to model and understand real-world phenomena. With their ability to describe the rate of change in various fields like physics, engineering, and biology, ODEs have significant impact on solving complex problems and making accurate predictions. Let's delve into the practicality and intense impact of ODE in real-world applications. History of ODEs. In-depth study of mathematics, ordinary differential equations have rich history and have been developed by differential pioneers from Isaac Newton and Gottfried Leibniz to Leonhard Euler and Carl Gustav Jacobi. These mathematicians made significant contributions to the understanding and application of ODEs. Their work laid the foundation for the practicality and intense impact of ODEs in real-world applications. Application 1. ODEs in physics and mechanics. ODEs are instinctively used in physics and mechanics to model various phenomena. They are used to describe the motion of celestial bodies, the behavior of fluids, the vibration of guitar strings, and the dynamics of mechanical systems. By analyzing and solving ODEs, scientists and engineers can understand and predict the behavior of these physical systems, enabling an advancement in technology and innovation. Application 2. ODE in population dynamics. ODEs are applied in population dynamics, a field that studies the change in population size and composition over time. By using ODE models, scientists have investigated how far factors such as birth rate, death rates, and migration impact population growth or decline. This information is crucial for policymakers and organizations to make informed decisions regarding resource allocation and conservation efforts. Application 3. ODEs in electrical circuits. ODEs are widely utilized in electrical circuit analysis, allowing engineers to understand and predict the various behavior of various components such as capacitors and inductors. By solving ODEs, engineers determine voltage and current relationships, analyze transient response, and optimize circuit design for efficient energy transfer. This application is vital in development of electronic devices, power systems, and communication networks. Application 4. ODEs in chemical reactions. ODEs play a crucial role in modeling chemical reactions. By utilizing reaction rate equations, scientists can study the dynamics of chemical reactions and predict how different factors such as reactant concentration and temperature affect the reaction process. This knowledge is essential for optimizing reaction conditions, designing efficient industrial processes, and developing new chemical compounds with specific properties. The study of ODEs in chemical reactions provides valuable insights in the field of chemical engineering and contributes to advancement in various industries. Challenges and limitations of ODEs in real-life scenarios. While ODE is a powerful tool in modeling chemical reactions, they have limitations in real-life scenarios. Some challenges include the assumption of well-mixed systems which may not accurately reflect complex systems. Additionally, ODE's model may not account for spatial variation or consider intricate reaction mechanics. It is important for researchers to be aware of these limitations and explore alternative models such as partial differential equations for a more comprehensive understanding of real-world applications. Tools and techniques to solve ODEs. There are various tools and techniques available to solve differential equations. These include analytic methods like separation of variables, integration factors, and variation of parameters. Numerical methods such as Euler's method, Runge-Kutta method, and finite difference method are also commonly used. Understanding and analyzing these tools effectively can assist in solving complex ODEs encountered in real life applications. Case study: ODEs epidemic modeling. Epidemic modeling is a practical application of ODEs. By mathematically modeling the spread of infectious diseases, we can analyze their impact and make informed decisions. This case study will explore how ODEs can predict the spread of epidemics, assessing the effectiveness of intervention and physical health strategy, public health strategy. Conclusion: practicality and future advancement in ODEs have proven to be practical and powerful tools for modeling real-world systems such as epidemic spread by accurately predicting the outcomes and impact of epidemics. ODEs can guide public health strategies and interventions. As technology advances, ODE application will continue to expand, revolutionizing our standard, understanding, and